Last part. Let's wrap this up. Okay, so what about amorphous polymers? We talked about um, inorganic glasses and metallic glasses. And so what about amorphous polymers? We'll get to semicrystalline polymers in a little bit. So if the temperature is low, significantly below the glass transition temperature, it acts as a brittle solid. We get a linear or nonlinear elastic region and fracture. If we're near the glass transition temperature, we get a viscous plastic flow and a more ductile, a little bit of ductile flow before we get fracture. If we're right at the glass transition temperature, something cool happens. We can get really extensive cold drawing, which is basically where we get significant chain alignment in the material, and we'll talk about this a lot more. If we're above the glass transition temperature, we kind of get a uniform viscous plastic flow. All right, so a fairly small temperature range here. In this picture, we're going from about 0.8 TG, slightly less than 0.8 TG, to 1.05 TG, right? And we get a huge range of mechanical behaviors over a very small temperature range. Okay. So something really cool that polymers do, right? I mean, you know, I'm a metals guy. Polymers scare me, but I think this is really cool. So polymers, amorphous polymers have this really cool thing where they can neck. So remember how we talked about elasticity in the polymer being an amorphous, and an elastomer, right, being an entropic kind of spring. This is kind of an analog to that, right? We've got a random kind of coiling of chains, right, with cross-linking happening. But we could apply tension to this, and basically you get a little region where the chains align that forms a neck, right? Now, normally in a metal, once you start necking, right, it's an instability, so it's going to break there. But in a polymer, this neck can grow, and so you have a region of more or less random chains outside the neck, and then inside the necked region you have very, very highly oriented chains. And if you pull this slowly enough, you can get really cool things happening. And we'll have a pretty cool demonstration of this in class. Okay. So, how does this happen? So, right here's the necked material. Here's the undeformed material. So basically we have shear bands, but they don't propagate all the way through. So we get shear band nucleation, right? And we get propagation, and all these shear bands connect into each other, right? And so this is the region, you've got this zone of material producing strain. Then in the neck you have this oriented material where you're pulling directly against the carbon-carbon covalent bonds of the backbone. So not much is happening here. All the interesting things are happening between this region of shear band nucleation in this zone of producing strain, right? The region where you start to go from the undeformed state into this highly oriented material state. Okay? So the stress at which these shear bands are going to initiate depends on the temperature and the stress state. Okay? So in polymers, the compressive yield strengths are significantly higher than the tensile. Okay? So what this really means is that under a tension load, you have a dilatational stress, which increases your local free volume, which makes flow easier to occur. All right? And so here we see in polycarbonate, the tension compression asymmetry. Here's the temperature on the x-axis. Here is the yield stress as a fraction of the shear modulus, and at a constant strain rate for all the tests. And you can see that no matter what the temperature, the compressive yield is always significantly higher than the tensile yield. So here we can basically have a yield surface, right? So this is the classical von Mises yield criteria, modified so that it has a pressure-dependent term. And so basically, anytime that this value, these are our principal stresses, anytime that the left-hand side is greater than the right-hand side, we're going to yield. Okay? So this is the first time maybe some of you have seen yield surfaces, but basically we've got a ellipse in our stress space. This is a two-dimensional picture of the yield surface, right? And if we're inside this, if our stress state, calculated from this equation, is inside the ellipse, we don't yield. If it's outside, we do yield. Now, yield surfaces, I didn't talk much about them for metals because they're kind of really an engineering idea. They're not really I would say, mechanics of materials, right? It's just a homogenized. They use just a very simple rule, and it just says you get flow and flow. When we were talking about crystal plasticity in metals, we were really talking about what was happening at the slip system kind of scale rather than the macro scale. But for polymers, these are really, really useful ideas because we only have the mechanism, the chain alignment, right? The shear banding and the chain alignment, and the macroscopic stress, right? We don't have the nicety of thinking about what happens in deformation in a grain, what happens in deformation at a slip system, and we don't have nice defects like dislocations to talk about how they're going to mediate the plasticity or carry it. So to describe what's happening, we really kind of have to resort to these kind of engineering ideas of a yield surface. So this term here, this pressure-dependent term, right? If we have a tensile load versus a compressive load, right, is going to shift. So for a tensile load, this is going to bias the yield surface in one direction. For a compressive load, it's going to bias it in the other, making this circle isn't exactly centered, this ellipse, right? It's going to shift on this axis, right? So that compression, right, this distance here is larger than this distance here. So you have a tension compression asymmetry. This is a demonstration of what happens when that pressure term is zero and you have equality. Okay. So that's that initiation of plasticity by shear banding. Another mechanism is crazing, right? And crazing are really ultra fine cracks, right, where the the long axis of the crack is parallel to the tensile direction. Right? So it's this microscopic region of highly localized drawing and nucleation of pores. So here's our loading in this picture here. Here's our loading direction. And basically what you have is these filaments that are highly drawn. So within these filaments, the chains are extremely highly oriented, right? And you have voids opening up, right? And the craze starts and then it grows. Here's the initial point. It grows in a direction that's perpendicular to the stress. Okay? So you've got these little tiny cracks. It's kind of like an array of, looks like little tiny cracks. Okay? And these are really limit the ductility. So it leads to fracture, right? Because now you can imagine the area that you have to carry the load is greatly diminished. So once these fibrils start breaking, right, your crack is just going to zip along your craze and fracture your sample. Okay. So we have a, you can imagine you're not going to craze under a compressive load, right? You need something ductile to open up those pores. Okay. So crazing is going to be promoted by a positive dilatational stress, and it's going to be inversely proportional to temperature. So you have a criterion right, an empirical kind of criterion that looks like this. And so you have a line on your yield surface here. So this is the envelope of yielding by shear banding. This is the envelope of yielding by crazing. So if I'm on this side of the line, I'm not going to yield by crazing. If I'm this side of the line, I am. So here, I'm safe from yielding by shear banding, but I'm outside of my crazing envelope. So what crazing does is essentially cuts off this top part of my yield surface. Right, so now my yield surface is given by this outline. Right, and this is just some experimental observation. So if you're in this region here, you're going to yield by shear banding, right? Because I'm under my craze yielding line, but above my shear yielding line. So that means I'm over in this region out here, right? I'm below crazing, but I exceed my shear yield surface. Out here, I exceed both crazing and shear yielding, so that means I'm out here somewhere, or out here somewhere. In this region, I'm within my shear envelope, but outside my crazing envelope, so that means I'm in this region here, so I'm going to fail by crazing. And down here, I'm safe, meaning I'm within this region here. This is just some experimental observation to show safe, yield by crazing, yield by only shearing, and yielding by both observed crazing and shear yielding. Okay, sorry for the cut. I got my tongue wrapped around itself trying to explain what was happening on this slide previously, so we'll take another stab at it. Okay, so we want to consider the effect of pressure on both craze yielding and shear banding. So imagine we have a stress state, a pure tensile stress state, right, in 2 dimensions. So we have on the diagonal sigma 1 and sigma 2, right, and they're both equal. So we're on this line. And sigma 3 is 0, right? So sigma 1 and sigma 2 are positive. So what's going to happen when we add a negative sigma 3 component to it? So we add something that's compressive in the sigma 3 direction. Well, so remember the hydrostatic pressure is the trace of our stress divided by 3. So if we add a negative sigma 3 component to it, we're reducing the hydrostatic pressure on our sample. Right? If we reduce the hydrostatic pressure, it makes it's going to create more free volume and make shear banding easier. So our yield surface is going to shift this way. Now, if we're compressive and sigma 1 and sigma 2 are negative, and we add a third negative component, it's going to decrease our free volume even more, right? So our surface is going to shift this way. The pressure has a greater effect on craze yielding, right? So if we add a triaxial stress state, if we add a negative sigma 3 component, we're really opening up a lot more free volume, right? And we can craze much easier, right? And in fact, without the addition of too much of a sigma 3 term, remember we're talking a negative term, so we're reducing the hydrostatic pressure, we can actually move the craze yield surface completely outside of the shear yield surface. So that means we will always fail by shear banding rather than fail by crazing. Okay? Play with this a little bit. Think about it from a mechanistic point of view as to what's happening. Okay, and to wrap it up, we want to talk about deformation of semi-crystalline polymers. So remember, back at when we talked about viscoelasticity, we talked about the structure of polymers, right? And we said we can get semi-crystalline by arranging. This is polyethylene. The chains in this way, and we get a unit cell here, right? And remember, we have an inherent anisotropy in our crystal properties because along this direction we're pulling along the carbon-carbon backbone. Along this direction we're pulling on the van der Waals forces that hold these chains in alignment. So we can't get a cubic polymer crystal because of the differences in bonding. Right, and these chains tend to fold back and forth, and you get these lamellar-like crystalline regions here. And we've got a whole bunch of defects, amorphous regions. We can have dislocations in our crystalline regions. We can have a whole bunch of other defects, imperfect fibrils, folding errors, amorphous regions that have short-range order, like the crystal highly correlated short-range order. But this is just kind of a reminder of the structure. So when we deform semi-crystalline polymers, this is nylon 6,6, the most common nylon, right? We have a we see behavior that looks like this. We have an initial yield and then a softening, and then a hardening behavior, right? And so this here, this region here corresponds to drawing. So here we have the highly oriented chains. So this is initial yielding. This is our drawing regime. And then this big increase here corresponds to when you are pulling on the elongation of the aligned molecular uh, structure. Right? And so for polyethylene, you can draw out to very, very high strains before you get to there. So this is out to a strain of 30, and we still haven't gotten to the stage 4, where we're pulling against the perfectly aligned structure, deforming the perfectly aligned structure. So schematically, what happens? Here's our crystalline regions, here's our amorphous regions. So as we pull, the amorphous regions basically stretch out, right? And they can't become fully elongated because there's cross-linking and other types of entanglements happening, right? But they stretch out, and if we keep pulling, the crystalline regions will break up by shear. Remember, these crystals are very strong this way, but this way they're only held together by van der Waals forces. And by doing that, it allows the amorphous region to stretch out even more. Right? So these are basically the stages of deformation in a semicrystalline polymer. So here we are in our highly oriented structure. Right? And we can also get, right, they're crystals, right? So we have defects. We can get slip in polymers, right? So we can get crystal shearing, right, which can give us stacking faults in our crystal. Here we can see we've got these folded regions, right? It'll be very hard to shear along this way because these folded regions get in the way. But if we have a region where we don't have a lot of folding, these crystallites can break up along this line here. And again, this is a schematic picture, but you can use it as kind of an internal mental model of what's happening in the polymer. Right? And so here is PTFE Teflon, right, with large crystalline regions. So this is a replica surface that we're looking at here. So what this is a surface, and then this is basically a carbon mold made to the surface. This carbon mold is then put in the electron microscope and to image it, because being non-conductive, it's hard to get good images of the polymer surface without having lots of charging. So the classic old way of doing it before things like environmental microscopes were invented was to make replicas of the surface. And you can see the alignment in the crystalline regions. Right, you can see the extent of the crystalline regions and amorphous regions. Now here they've deformed to a plastic strain of 70%, and you can see that the crystallites have fragmented basically. They're not extended crystalline regions like you see here, and you can also see what are potentially slip traces in the crystalline regions. Okay, and as we draw, right? So when you start out, the polymer is basically going to be pretty isotropic. So lambda of 1 is this curve here. This is the modulus along the x direction, the modulus along the y direction, modulus along the draw direction. right? And as you increase, you develop anisotropy, right? Your chains become very highly oriented. So you get a much stiffer along the drawing direction than along other directions. Now something curious happens here, right? Notice initially, when we first begin to draw, we go from an extension ratio of 1, which means no deformation, extension ratio of 1.4, which is basically about a 40% strain. We've weakened our elastic stiffness, and then it starts to get higher. Right? We've weakened in all directions at 1.4. By the time we're at 2.4, we've exceeded along the drawing direction and the perpendicular direction, but at a 45-degree angle, we're significantly weaker than where we started. Then by the time we get out to 4.6, we've got a lot more strength along the, a lot more stiffness along the drawing and perpendicular direction, but a lot weaker at a 45. So this is something I want you guys to think about. What's going on here? Why does it follow this pattern? Right, and we'll talk about that in class. Okay, take care. Have a good week and weekend, and we'll catch back up with more lectures next week.